The Bohr model of the hydrogen atom is wonderful because it's a simple formula that you can write down on a 4x6 card for the exam, and you can get very accurate, correct answers without any kind of fancy mathematics at all. That's the only one that I'm going to require you know for the exams. However, I did show you in an earlier lecture the more complicated electron orbits that happen even in something as simple as a hydrogen atom. They're described fairly well by the Bohr formula, but there's more information. In particular, the extra information in there is about the orbital angular momentum. Remember, this is just an approximate classical description, not really what's happening in quantum mechanics. But still, the electron, as it goes around the nucleus, has a certain amount of angular momentum around the nucleus. And this remarkable insight that quantum mechanics, including Bohr, had was that the amount of angular momentum cannot be any possible value it wants to be, like a planet orbiting the sun. It's only quantized into fixed amounts of angular momentum in units of Planck's constant h divided by 2 pi, it turns out. You don't need to know that. So for you to understand anything more complicated than the hydrogen atom, I don't really expect you to know any of the mathematical formulas, but I want you to have a qualitative understanding here of what happens when there are more electrons than just one in atoms. So the good news is that things are not all that different from what we've seen in the Bohr atom. So let's look at that for the moment. This is a rather complicated, messy table that I don't particularly want you to memorize anything about it. I just want to show it to you. Let's look at the first several lowest energy possible electron orbits of an electron in a hydrogen atom. Well, here is our most important quantum number, the energy level, n equals 1, 2, 3, 4, and it just goes on up and up and up to hundreds until the electron is in such a large orbit that it's practically not connected to the nucleus at all and it just escapes. But these are the ones we're going to be interested in. And so as advertised, what is the ground state here? N equals 1. That's the lowest energy. Right? According to the Bohr formula for hydrogen, it's minus 13.6 electron volts, 13.6 electron volts below the energy it takes to completely free the electron and escape. And there's only one possible orbit for an electron in the ground state. It has no angular momentum. L is the angular momentum. There's no there's no orbital angular momentum there. It's just a spherical looking orbit. You go back and look at the pretty pictures that I showed that show the probability distributions of electrons. Totally spherical, concentrated in the center around the nucleus in a very tight orbit. Now, the next first excited level, the n equals 2 energy level, is a good bit higher up. And it turns out there that you have a very simple one, which is, again, spherically symmetric, but it's further out. It's a larger average radius that you would expect to find the electron. Also, there are 3 other possibilities because the orbital angular momentum of the electron may not be 0 in such a case, but it can have only 3 possible orientations, and no other orientations are possible. So that corresponds to these are the different orientations of angular momentum. You don't need to know that. Then we have a third energy level, n equals 3, which again could either be no angular momentum, just a spherical one, or we can get these fascinating little quadruple patterns and so on as more angular momentum from the orbit of the electron around the nucleus comes into play. And you get more and more ornate and elaborate probability distributions that I showed you before. But there are only, these are like standing waves. There's only a fixed number of possibilities here. So let's look at that. The way I guess chemists sometimes describe this is 1 is the quantum, most important thing, the quantum energy level, 1 being ground state, 2 is the first excited, 3 is higher, 4, and so on. And then, depending on how many units of electron orbital angular momentum are, if there's none, we'll call that a s orbit. If there's 1, we'll call it a p orbit. That's all that's possible, up to 2. For n equals 3, you can have 0 units, 1 unit, or even 2 units of angular momentum. That would be called a d. And if you want to go on with this, if there's even more angular momentum present, we call that an f orbit. Well, those are the possibilities. Now, an electron in hydrogen can go into any one of these. Could be in any one of these orbits, and that's fine. It's happy. It just takes more energy to jump up from 1 to 2 to 3 to 4. This is a detail, in hydrogen, it's so simple and so symmetric that the amount of energy above the ground state is pretty much the same whether it has angular momentum or not. That's a very small difference. So both of these, for example, are about 10.2 electron volts above the ground state here. Doesn't matter in that case. And then all these n equals 3 levels have the same energy as given by the Bohr formula that you now know. In other atoms, though, there'll be more, of course, electrons in them, and the outermost electron, that's the one that we're really concerned about, the one that's the furthest out, that's the least tightly bound to the nucleus. Depending on how much angular momentum it has here, if you make an energy level diagram, remember those energy level ladders? These different angular momentum states will have somewhat different energy levels in them. This one might be a little bit higher than that one, for example. And this one might be higher than this one and this one. So now there are suddenly far more possible energy level differences. Some of these steps that were all at the same level, all these n equals 3 steps, in other atoms and other elements will split up into 3 little steps, and then this one will split into 2 little steps. And so you can see the more steps I have, the more possible energy differences there are between all of these multiplying energy levels. So you get a much richer spectrum with more possible transitions than we just have with that one boring electron in a hydrogen atom. So that's what I wanted to show you to start with. Now, I'm sweeping a lot of mathematical details grossly under the rug here to just give you the flavor for this. When you start adding more electrons to atoms that have more plus charges in the center, helium has 2 plus charges, and so on, carbon has 6, I'm starting to add more electrons. If it's electrically neutral, it should have as many electrons as protons. And so the electrons will tend to go into the lowest energy orbits that they can find. But pretty much this description that was inspired by the Bohr atom here is going to give us a pretty much fairly accurate description. It's at least a qualitative description of where the electrons are going to go when there's more than one of them in a more complicated atom than hydrogen. Now I'll show you a real detailed table that actually this gives me a headache too. So don't even worry about the details of this table at all. I just want to show you qualitatively what's happening so you'll be a little bit familiar with the lingo when you hear this in the future. You probably will hear this in the future. Certainly in a chemistry course you would. So here we have descriptions of what the electrons are doing in atoms in the periodic table, starting with the simplest one, 1 proton hydrogen, 2 protons helium, 3 lithium, 4 beryllium. Atomic number, that's the number of plus charges, protons, in the nucleus, which determines what element it is in the periodic table, up to 6 carbon, and so on. Now what's happening here in the ground state? That's, it says here, ground state. What is the electron orbit in the ground state? Well, we already know for hydrogen, that's a Bohr formula, it goes to n equals 1, and there is no angular momentum, so it's called the s orbital there. It's a nice spherical little simple probability distribution we saw. How about helium? Interesting point here. Helium can have 2 electrons in the n equals 1 configuration, both with no angular momentum. What's the difference between these 2 electrons? A little 2 up there means there's 2 electrons here. The only difference is that electrons, it turns out themselves, in addition to orbiting around in the atom, so they have some orbital angular momentum. They also, electrons are like little spinning balls. It's just it's a quantum mechanical version of that. Don't think of this as a billiard ball that's spinning, but it does have angular momentum, and remember that has to be quantized too. So the spin angular momentum of the electron is very simple. It can either be up or it can be down. Those are the only two possibilities according to quantum mechanics. No other possibilities allowed. But those possibilities are allowed, and they both have the lowest energy. So helium is pretty similar to hydrogen. You have both electrons in the ground state. One would be in n equals 1. They have 0 angular momentum, except the only difference is one of them spinning up, one of them spinning down. Hooray. Now we run right smack into one of the most amazing principles, or strongest principles that I know of in all of physics, which is the Pauli exclusion principle. And the Pauli exclusion principle says that under no circumstances, absolutely positively never, ever, will any two electrons in an atom be allowed to share the same orbit. They absolutely will never do it. Just to show you how strong a matter of principle this is, if you were to somehow try to force two electrons into the same orbit, to try to violate the Pauli exclusion principle, it'd be really bad. I mean, these electrons are electrons of principle. It reminds me, I don't know, of some very stubborn particles. If you like those samurai movies, it's kind of the same thing. They're very stubborn and very proud. They stick to their principles about loyalty, honor, clan, and so on. And if you try to get them to violate their principles in an intolerable situation, electrons, just like the samurai in all those movies I've seen, would rather choose self-annihilation. They will actually destroy themselves rather than violate the Pauli exclusion principle. Again, UCLA folks, please notice this is not a UCLA place. Pauli did not endow our basketball auditorium, although there is kind of a Pauli exclusion principle which operates in somewhat the same way in Pauli Pavilion. Every seat you can think of as a possible energy level, a possible electron orbital configuration. I've got S's, P's, they even have identification. Wouldn't it be funny if Pauli Pavilion had S seats and P seats? I guess it would be the higher up sections, and F and D seats and so on, and 1 would be right by the court side, 4 would be up in the rafters and so on, and you have a ticket for each one of them. And the principle in Pauli Pavilion is, the Pauli exclusion principle is 1 person per seat. The people come in like electrons. The first electron probably goes right to that courtside seat right there, but then a second one gets this seat. Then the other electrons that come in will have to get higher up seats. Yes, that's right. They'll have to go to higher energy orbits if we're talking about the Pauli exclusion principle for electrons. Somewhat analogous. I hope you can remember that now with all of that lame UCLA metaphor. So I've pretty much filled up everything at helium in the lowest energy ground state. N equals 1 is full, and there's no more seats. I'm sorry, there were only 2 seats available for there. However, we could put another electron that comes along. We want to have a third one in lithium. We're going to have to put it in the second energy level, N equals 2. And again, the lowest energy version of that will be no angular momentum, so let's put an S. We can put 2 of them in there because I could have 1 0 orbital momentum, but with energy level 2 up, and then the other spin of the electron could be down, so I can stick 2 of them in there the same way I stuck 2 in the 1s. And then I'm full there. Now I can start putting some in that have angular momentum. So 1 unit of angular momentum, we'll call that a P. And remember, there were 3 different orientations, 3 different quantized values of that angular momentum, basically 1, 0, or -1, and then times 2 electron spins. So I've got 6 possible combinations, 6 ways that an electron cannot violate the Pauli exclusion principle, can actually be in a different energy orbit, a different state, until I get up to here. So now I've filled up everything in the 2p level, and now I'm sorry. N equals 2 is completely full. There's no more places for electrons to go. The next electron that wants to come along, if I want to have 11 electrons, for example, in a sodium atom, it's going to have to go up to n equals 3. Very uncomfortable there. That poor little electron just hanging around all by itself at a high energy level that it didn't really want to be in, because sections 1 and 2 just got all full. So let's look at this now. I've put some lines here in this diagram to where the particular energy level got all full. It was all sold out, all the seats occupied. After just only 2 electrons arrived, the n equals 1 was completely full, and we had to kick people up to n equals 2 section. That was helium. Totally full, no room. All right, so we started filling up the second section, the second energy level, with more electrons, and then that got completely full right up at neon. We had 10 total electrons. That's 2 on the n equals 1 level. It's called the K shell. And then 8 more in the n equals 2 shell. That's the n equals 2 level, which is called the L shell. Just giving you some lingo here for chemists. Apparently chemists don't really know the alphabet very well, because the first one's K, then L, M, N. Don't know what the history of that is. I don't know why they didn't start with A. Maybe it was made up by Germans or something. I don't know. Sorry. Neon is the last one that doesn't occupy in its ground state the n equals 3 level. So then now we're filling up the n equals 3 level. And again, we're pretty much up to 0 angular momentum gets filled up first, then 1 unit of angular momentum. We got 6 of those possibilities. And so the next shell here, it's called a shell when you fill them all up, the n equals 3 shell gets full by the time you get 18 electrons in it, totally full up. It's very happy like that. And that is argon. Potassium, though, bummer. Potassium has one little lonely electron that had to get put up there in the n equals 4 level. Not such a happy energetic state. It's at a much higher energy level than it would like to be at. All the others have close seats. It's up there in the n equals 4 seat. Not so happy. Notice what happens here. Every time an electron shell corresponding to n equals 1, the lowest energy, n equals 2, next up, n equals 3. Every time it gets completely full with all the possible electron orbits occupied and no room for any other electrons on account of Pauli exclusion principle, you get a very happy, very chemically stable atom. Now, for the next 3 minutes, I'm going to summarize my understanding of chemistry. This is chemistry in a 3-minute summary, and then we're done with it because this is a physics course. What is the physics basis when you understand atoms and atomic structure, and it's all about electron orbits and electron energies? Then that basically is all of chemistry. Well, all of chemistry, to start with, everybody knows that when you have a perfectly filled up set of electrons, that atom does not want to give up electrons, it doesn't want to share electrons with anybody else, and it doesn't want to accept electrons from any other atom at all. It has no interest in that. Energetically, there's just no gain to be had by that. So that is true for helium. Oh, look, it's also true for periodic element number 10. Neon, also completely full shell there, doesn't want any more electrons, doesn't want to give up any more, it wants to stay by itself. We go up to n equals 18, Z equals 18, 18 plus charges, 18 minus charges. Those 18 electrons have filled up a shell completely, so none of these so-called noble gases, helium, neon, and argon, none of them want to have any chemistry. They don't do any chemistry, they will not. Virtually impossible to make them do it because the electrons are happy and full. They filled up their shells and they don't want any more. Contrast that with, for example, let's look at an atom which is just one beyond the noble gas neon, sodium there. Sodium, as I said, has this unwelcome, extra outsider electron number 11 in a rather high energy state, just all by itself there. That's energetically not favored, but it had no choice. That's Pauli exclusion principle says that's what sodium's going to be. Contrast that with the atom just before argon, almost complete. Oh, darn. It was almost filling out its entire second shell, the L shell. except it's missing one electron. I wonder how it feels to be a chlorine like that. All of your second shell is full, except you're just missing one little electron to make you complete. That's chemistry, actually. The fact that some atoms have extra electrons that are unwanted, whereas other atoms could be completed, or more completed, if only they could gain an extra electron. I think some of the atoms up on this left side of the periodic table, and the periodic table is very suggestively drawn up so that everything on the left has a few extra unwanted electrons. Everything on the right has a few missing electrons. If only they could get an electron from somewhere, maybe from somebody on this side, they could be happy. They could fill up their shell, which would be energetically favored. And that is exactly my description of chemistry. So I'll show you, here's one example of it. Not to scale, but it's got pretty much everything going on. There we have sodium, all the plus charges in the center, all the protons and the neutrons to hold it together in there. The inner shell, that's your n equals 1. You've got just the up and down electron spins, zero angular momentum, that's all. Then we've got, let's see, 8 more here in the next shell up. That's the L shell. We saw that that could have 8. You could have 0 angular momentum, plus 1 or minus 1 angular momentum, and then there's pairs of them because the electron spin can be up or down, and that's all full there. Sorry, 2 plus 8, that's 10. Uh-oh, and there's one more, making it the 11th atom in the periodic table. One more that didn't really want to be there. Now look at chlorine. This next shell is actually quite loaded up now. Instead of having, let's see, we've got 10 in the center, 11, 12, 13, 14, 15, 16, 17. Aha! Almost up to 18. There's this one gaping hole here where an electron would be very welcome to join. This electron would be very welcome to leave. So what energetically happens? What actually happens if these two atoms get close to each other under the right conditions, as long as they're not being smashed together too hard, but just hard enough that they could come close to each other, they will recognize that the potential energy of this electron would actually be lower. It could go down from this high energy level to a lower energy level if it could spin around the chlorine instead. So this actual configuration here would result in a lower total potential energy. You see, this sodium would act more like a neon here. It would be 10 electrons, both shells perfectly full, and this chlorine would act more like an argon. It would fill up here. What's happened right here? They got close enough so that the electron, what a fickle electron. It it's like, went to the prom with the sodium atom, but it ended up spending most of the time at the prom with the chlorine nucleus for whatever reasons. I think we've probably all had this experience at our high school proms, for example, in 12th grade, with one particular date that acted just like this electron. Now I understand it much better than I did, when I was 16 or whatever. Anyway, it's the same thing with electrons. They just go where the energy is lower here. And now what you have is a sodium ion. It has a plus charge because there's one more proton in here. All right, 11 protons, only 10 electrons, so that's a plus 1 charge. Meanwhile, the chlorine is an ion also. It has an extra electron, so this has a minus 1 charge, one more electron than proton. This is an ionic bond, and so clearly the electric attraction between the sodium and the chlorine, which are sharing an electron. Ooh, that sounds a little bit more interesting than my prom night here. The electron has made an ionic bond because there'll be a very strong electrostatic attraction between the plus sodium and the negatively charged chlorine ion there. That is my understanding, that's an ionic bond. This is a very strong one. Oh my gosh, it makes salt. Pouring salt in the wounds there. I've totally gotten over it now. That was so many years ago. Don't even remember her name. Yeah, right. And so all other chemistry, as far as I'm concerned, is just atoms that want to get rid of electrons, sharing them, forming molecules with other atoms that want to receive electrons. basically on the right-hand side. So you've got donor atoms on the left side of it, and then recipient atoms on the right side of the periodic table of elements. And that's how molecules form. It's why molecules would be preferred to form under the right conditions if sodium and chlorine can get close together. In fact, this is a pretty stable molecule here, sodium chloride, salt, unless collisions were so violent at high temperatures that these two atoms might be knocked apart by a very high energy collision. And that could happen, for example, in a flame. If you get up to 1,000 degrees, the electrostatic attraction is strong enough to hold these together at room temperature, but at high temperatures it might not. In the sun it certainly doesn't, and we see individual sodium atoms there and individual chlorine atoms. That's pretty much all I want you to know about chemistry. Wasn't that easy? Now, you don't have to take inorganic chemistry. At least you don't have to take it from me. Thank goodness for that.